I'm sharing my screen. All right. No. Uh-oh. Shouldn't have started the recording. I can post them, but I'm also just grabbing them from the textbook. I didn't finish all the chapter 7 notes. I only did them for today. But I posted, I'll show you where the probably, or like essentially. Most importantly, Pi Day tomorrow. Happy Pi Day. Since I won't see you, can celebrate tomorrow. But sorry, I totally forgot. But you can grab the entire textbook, or I posted only the sections that we're going to cover, and then you can snag stuff from the textbook instead, which is what I'm going to be doing today. We've got some administrative notes because we start a new chapter today. It's all kind of faint, but sets and counting, pretty fun, leading us up to probability eventually. But today we just need to introduce a bunch of terminology that I need you to have a good handle on so that we can talk about, sets properly. Okay. And so a lot of terminology today, and then just kind of looking at what does it mean. And then that's pretty much it. Venn diagrams, if you've used a Venn diagram, great for jokes too. So, all right. And then we move into tree diagrams and the multiplication axiom, permutations. And then here's where I went rogue. And I decided, nah, we're not going to do circular permutations and permutations with similar elements. Let's cut it. Because we'll have done permutations, and that's fine. We are going to do combinations, but we are not going to do combinations involving several sets, and we will not be doing the binomial theorem. Wow. Then we've got test number 2. Wow. Just steamroll right ahead. March 27th? Oh, I guess it's on Moodle. I think it's the 27th. So we will do combinations on the Tuesday before, and then we'll have the test on the Thursday. I don't feel too bad though, because it's not before a long weekend. That was our stumbling block last time. But March 27th, and it's going to be on chapter 6. We didn't do 6.6 explicitly, but you can do it because it's just an overview of the different types of financial math problems that you could solve, right? So you could do 6.6 as well. But I felt I did a reasonable job, so I skipped it. So it's going to be on chapter 6 and 7.1 to 7.3 and 7.5. As promised, I'll just take questions from the textbook questions. So you can have seen them. And I'm playing around with an idea where you guys make me a test. I think it's a good exercise in thinking about, okay, well, what could she possibly want me to show her that I know, right? Kind of flip it a little bit. And so I think that's an interesting exercise, but I haven't fine-tuned it yet. So it's just an idea that I have. Right? Have you guys make practice tests instead of me. Okay. I think that was all my admin. Did I have more? Admin, paperwork, paper shuffles. Oh. Okay. So 7.1, sets and counting. So like I said, there's going to be a lot of terminology that we need to get a handle on. And of course, we start with a set. Okay. And so, oops. Set operations and set notations. And so a set, and this is just all out of the textbook, the first little bit here. Well, it's always out of the textbook, but all these definitions are just first couple of pages. But a set is a collection of objects, okay? And its members are called the elements of the set. Right? And so you can have a set of Pokemon cards, right? And each card is an element. Okay? Now, how you denote a set is we tend to use capital letters, okay? And even more picky, we tend to stick to the beginning of the alphabet unless there's a reason to use a different name. Okay? And so A, B, C, for example. Okay? And then we list all the members or the elements of the set in braces. Okay? So curly braces indicate that you're talking about a set. Okay? And so if we list the members of the chess club, well, the members of the chess club as a set, which we could denote by a capital C for chess club, I guess. Curly brackets tells me that this is a set. And the elements in this set are Ken, Bob, Tran, Shanti, and Eric. Okay. So these guys are the elements. And, oh man, that's annoying. I'll try to hold it down. And this whole thing is the set. Okay. So C is the set of Ken, Bob, Tran, Shanti, and Eric. Okay. It is possible for a set to have no members. Okay. And we call that the empty set. Okay. And the empty set is denoted by this kind of zero with a slash through it. Okay. And so that's not something I expect you to know. And it's pretty common to write your zeros with a slash through it. But now that we've introduced the empty set, right, this is not the same thing as a zero, right? In fact, a zero would be an element. Okay. And so here, I'll say note, the empty set is not the same as zero. It is not equal to zero. The empty set looks like this. Curly brackets, nothing in there. It's the empty set, no elements. A lot of these definitions are intuitive, right? If you just kind of let them be, okay? And so two sets are equal if they have the same elements, right? Has to be exactly the same, right? But it's one of those things where it's like, oh, what does it mean for them to be equal? Well, it means they have the same things in there, right? And so, but I will add have the same elements, and I'll add exactly the same. Set A is a subset of a set B, right? And if you just kind of remove yourself from the definition, right? If I give you a stack of playing cards, right? 52 playing cards, and I ask you to select a subset, what would you do? you would select a smaller set, right? And so it's just pulling from that bigger set. So set A is a subset of a set B if every member of A is also a member of B, right? So A is pulled from B. Right? And so if we have a set C, Al, Bob, Chris, David, and Ed, A, B, C, D, E, that's convenient. Okay. And A is going to be the set of Bob and David, right? Well, Bob and David are both in this set C, right? And so then A is a subset of C, okay? And how we write it is like this. A is contained in the set C. Okay? And so here, you're going to read it as A is contained in C, right? Or A is a subset of C, that's proper as well. Or A is a subset of C. But that C, right, the kind of C with a line underneath it just means that it's contained in C. Here's where it gets a little bit boggy. Every set is a subset of itself, right? If you have a stack of playing cards or an entire deck of playing cards, 52 cards, then one possible subset that you could grab is the entire deck, right? There's no rules against that. Okay. But also, the empty set is a subset of every set. Okay. Which means that, okay, well, one of the options that you have when you're drawing a subset, right, of undefined size from a deck of cards is you could choose to draw no cards, right? That's an option. And so that would be the empty set. And so these two are kind of curveballs, right? Every set is a subset of itself, and the empty set is a subset of every set. We've got examples later, but we're gonna roll through these terms first. And there's a LaTeX typo in here, but we'll sort that out. Let A and B be two sets. So we use kind of generic A's and B's to denote sets. And then the union of A and B, which is written as A, and it's kind of a U. And this is the union. If you prefer to read it as or, that's fine. So sometimes or often, I just kind of read it as or. Right? So if it's a proper U, A or B, okay? Just because that tells me a little bit about what this union is. So this new set of A union B or A or B is the set of all elements that are either in A or in B or in both A and B. Right? That's kind of the part that stumps people a little bit, is that it can be in both A and B, right? If there's overlap, and that's okay. This should just say B. Okay. So the union of two sets, right, is then I have A or B. Okay, so it's allowed to be in either or both. Versus the intersection, if I have A and B, two sets, then the intersection of A and B, okay, which is written as an upside down U, okay, this is the intersection there was, oh, there. I had MacGyvered it so nicely last day. Better? So an upside down U is the intersection. Okay. And how I read it is as and. Okay. And so the intersection of two sets is the set of all elements that are common to both sets, A and B, right? And so it has to be the overlap, right? So this we can think of as the overlap. So far, so good, I think. The universal set is denoted by a capital U, not to be confused with the union, because the union is not a letter, it's a logical, I don't know what to call it, set notation. Whereas a capital U is the universal set. Now the universal set is the set of all elements under consideration, so all possible elements. Okay. All possible elements. If we let A be any set, then the complement of a set A, in this course, we're going to be writing it as A with a bar over it, and I read it as not A. Okay. It's possible that you may have seen A to the power of C for the complement, but you can read either one of these as, I read them as not A. Okay. So it's everything in the universal set that's not in A, right? That's the complement. Okay. And so the complement of A is the set consisting of elements in the universal set U that are not in A. So you just take away, right, everything in A, and then that's the complement. The definition of disjoint sets, or mutually exclusive, right? Those we throw that around a lot, right? Well, those two things are mutually exclusive, meaning what? Meaning they can't happen at the same time, right? There's no overlap. Okay. And so two sets A and B are called disjoint sets if their intersection is an empty set, right? And so here, I'm going to elaborate. Oh, of course I did that. Okay. Or mutually exclusive. And so here, it means they have no elements in common. Right? If the intersection of A and B is the empty set, it means that they have no elements in common. And so then they're disjoint. A set and its complement are disjoint. But two sets can be disjoint and not necessarily be complements. And so we'll explore that in some examples. let me smush all these together.
Can we see the last three definitions a little bit?
You got it.
All right, I'll get it.
I don't know, I can't tell. It's kind of. Everyone's like, yep, got it. Okay, now we're ready to do stuff. We're gonna work through lunch. List all the subsets of the set of primary colors, red, yellow, blue. Now for simplicity, let's abbreviate this RYB because I don't want to write all those out, right? So my elements of the set are red, yellow, blue. So a possible subset. Well, let's get the ones that sneak under the radar out of the way first, right? Because we just established that the empty set and the set itself, those are always subsets, right? Possible subsets, but they tend to sneak under the radar. So we'll start there. And then the set of RYB. Now I tend to do these kind of somewhat methodically, right? Start with my R combinations and then move on to my Y combinations. And one thing to note here is that the order of the elements doesn't matter. I'll also point out that if there are duplicates, which we won't have until later, but if there are duplicates, we only write them once, right? So if there are duplicate elements, we only write them once. Oncey? Once. Let's start with, here's my set, right? And I'm drawing subsets. Let's draw subsets of size 1. Fair enough. First option, I draw red. Or another option, I draw the yellow. Or by that same logic, I draw the blue. These are subsets of size 1. How about subsets of size 2? I could draw red and yellow. Or I could draw red and blue. And if order doesn't matter, I'm out of options for the 2. I could do yellow. I've already got red and yellow, which is going to be equivalent to yellow and red because the order of the elements doesn't matter. And so the only combination that I don't have is yellow and blue. Here's a fun fact that's not in the textbook. An LFF, a little fun fact. Any set with n elements is always going to have 2 to the power of n possible subsets. Huh? Any set with n elements has 2 to the n possible subsets. Can confirm. We had 3 elements, right? So n is 3. And so here we have n is equal to 3. So we expect 2 to the power of n. So we expect 2 to the n, which is 2 to the 3, which is 8 subsets, or possible subsets, I'll add. That's just a fun fact, but it is a nice way to be able to check to make sure that you got all your subsets. But also, this was only 3 elements, right? And we can check, do I have 8? 1, 2, 3, 4, 5, 6, 7, 8. Phew. Yeah. Even at 4 elements, the possible subsets, right? 2 to the power of 4. It's terrible. 16. 5. No thanks. Not today. I'm going to see if I can grab all of the, oh, maybe not that. I did not have enough time to organize these or post them clearly. Sorry about that. If F, the set F is, can I just call them A, J, R, S, and Y? Instead of reading out these names. Usually these sets are, or these elements are numbers, right? But it's easier to think about words, I guess. Eichmann, Jackson, Rice, Sanders, and Young, and let B be the set of Griffey, Jackson, Sanders, and Thomas. Find the intersection of the sets F and B. Let's start with putting this into set notation. And so what I want is I want the intersection, which is that upside down U. Because the union is the U, and then the intersection is the other one. You only need to remember one. Okay. I also like to remember it because this makes kind of an A, right? And I read it as and, just to nudge me in the right direction of, okay, it has to be in both the set F and B, right, to get those elements. I should erase that though, because it's not quite true, but. So now the intersection of F and B is going to be the list of elements that are in both, right? And so Eichmann, I don't know how to say these names, is not in B, so I'm going to scratch them out. Jackson is in B, so I'll write them down. Rice is not in B. Sanders is in B. And then young is not in B. Do you need to check B? Do the same thing? Not really, right? Because you already went through all the elements of A, and if they're not in both A and B, then we don't care about them, right? And so you can do it for completeness if you want. Oh, here come my bad curly brackets. My left one's always nice, my right one is never nice. But I just kind of go for it. Okay. So that is the intersection of those two sets. Find the union of the sets F and B, where F and B are given here. Now the union is the or, right? And so here the union, I think of it as or. So first, in terms of notation, what are we being asked to do? We're being asked to find fub. No, I read it as F or B. I should make that a nicer union, right? F union B. So now we're going to list all the elements that are in F or B or both. Okay? But the only thing is we don't list the duplicate elements twice. We only list them once. Can I do just A? Usually what I do is I list all of F, and then I go ahead and I list all of B and either remove duplicates right away, or I look for duplicates and I eliminate them afterwards. A, J, R, S, Y, being lazy. G hasn't been listed yet, but Jackson was listed, Sanders was listed, and let's add Thomas to the list. So the union of two sets is always going to be bigger, right? Whereas the intersection is always going to be quite small. If we let the universal set U be Roy G. Biv, colors of the rainbow, red, orange, yellow, green, blue, indigo, violet. Yeah. And then P is going to be the list of primary colors, red, yellow, blue. We're going to find the complement of P and also practice that notation. Right, the complement of P, we denote it by writing a P with a bar over it. The complement of P is going to be the universal set minus P, right? Or what we could do is we can go through and just kind of scratch out red, yellow, and blue and list the remaining colors. It's going to be the set of orange, green, indigo, and violet. So really what we're going to say here is that the complement of P or not P is going to be the universal set minus P. Just take away the ones you don't want, right, which is all of P, and then you're left with everything that's not P, right? Yes. I was just getting excited because it's kind of a thought exercise coming up. If we let U be Roy G. Biv again, and P is the set of primary colors, find a set R so that R is not the complement of P, but R and P are disjoint, right? Just kind of linking up our definitions that we've seen so far, right? What does it mean to be disjoint? It means they have no elements in common, right? It means that R and P, right? The intersection of R and P is the empty set, right? That's what it means to be disjoint. So we want to find a set R, and we've got some options. But the elements of R can't have any elements in common with P. But it also can't be the entire complement. But what could we do? We could take subsets of the complement of P, right? And so any subset of the complement of P excluding the empty set and the complement of P itself, we tend to call those proper subsets, but that's okay. We don't need to know that. So any subset of the complement of P will satisfy this criteria. For example, we could let R be orange and violet, oops, round bracket. Or R could be green, indigo, violet, something like that. Because I'm pulling from the complement of P, I know that there's no overlap with P, right? But I also wanted to make sure that R was not just the complement of P, it had to be a subset. And so, nice. We leveled up pretty quick here. If we let the universal set be Roy G. Biv, P is the list of, or the set of primary colors, red, yellow, blue. Q can be a set of red and green. And R can be a set of orange, green, and indigo. What we want to find, and probably the first step is just deciphering this thing. We want to find P or Q, but the complement of that and the complement of R. just like algebra, we need to break this down into steps. Now, you'll want to do the complements before you do that intersection, right? And before you can do the complements, right, in the case of P or Q, you'll want to find P or Q first, right? And so we break this down, I'll say to find. We need to break it down. Break it down. First thing we're going to do is find P or Q. The union of P and Q. The union of P and Q, or that's why I like to read as or, because that's a reminder to me that, okay, any element in P or Q or both, they're going to be in this set. Okay. And so what is in P or Q? P is red, yellow, blue, and Q is red and green. And so I'm not going to list red twice, but I will add green into the mix. Okay. And so this becomes R, Y, B, and G. That's the union of P and Q. Now, I'm going to take the complement of this thing. The complement is the universal set, but take away P or Q. And so it's everything that's not in P or Q. And so I'm going to go through my universal set, right, and jot down all the colors that are not listed in my P or Q set. And so I'm going to start, red is not one of them. Orange is, yellow's in P or Q, green's in P or Q, blue is in P or Q, and then indigo and violet are the new additions. So you want to build out those complements before you can do the intersection of the two. Same thing with the complement of R. The complement of R is everything in the universal set that is not in R. And so we do the same thing here. R is orange, green, and indigo. And so in the universal set, I have red, can't do orange, yellow, not green, blue, not indigo, and violet. Now, what color can I use? Purple. I'm ready to do this whole thing because now I've created, this is just a new set and my complement of R is another set. Now I'm ready to take the intersection of the two, which is what? It's going to be all the overlap or any overlap. And so now we're ready to find P or Q complement and the complement of R. Only overlap is allowed, right? And so I don't have orange in the complement of R. I don't have indigo, but I do have violet. So, hey, cute. And I wrote it in purple. Close enough. That was a fluke, but still I'm happy. So given small sets, we can do set manipulations. Taking some practice. I even caught myself doing it, right? When I was describing the disjoint sets, right? No elements in common. How we visualize sets is usually using a Venn diagram. And so a Venn diagram, let me just copy and give myself some space here. Whoa. Okay. Okay. And so a Venn diagram represents a set as the interior of a circle. So we usually use circles, right? And so often 2 or more circles. Now we're gonna cap out at 3, but that's okay. You could do more, but they become very complicated. Okay, and so we'll do 2 or 3. Okay? And they're going to be enclosed in a rectangle where the rectangle represents the universal set. And so usually how we write that, or draw it rather, is like this. So I have a rectangle, and somewhere here, usually in a corner somewhere, I denote that that rectangle represents the universal set. Now, when you're getting used to Venn diagrams, it can be counterintuitive, but even if a space or a circle has no elements, we still draw it, and then we just don't put elements in there. And so if we have a set A and a set B, this is for 2 sets. It's possible or potentially possible for an element to be in the set A, but in order to be in A, it has to be in the universal set. So A is a subset of the universal set. And we could have elements that are in both A and B, unless they're disjoint, right? Then they would be separated, but usually we just leave the space blank in that case. We could have elements in B, but not in A. And we could have elements that are in the universal set that are not in A nor B. I do want to just introduce here a Venn diagram for 3 sets, what it looks like. And you've probably seen it, where the universal set, and we have sets A, B, and C. Great for jokes. Right. What do all these things have in common, right? Or what elements of a set do they have in common, right? And so kind of a generic 2-set Venn diagram and a 3-set Venn diagram. Let's give me some more room here. and maybe a lot more room. Because what I want to do is at least try our best to draw those definitions that we had, right? And so, oops, our definitions. What was our first one? I think it was the union. Got to go way back up there. The set and the elements, the empty set, two sets are equal, subset. Let's do the union. A or B. In terms of a Venn diagram, our universal set, oops, I don't know why I did A first, AB. If it's an A or B or both, right, then we're going to be talking about this entire area, right? It can't be outside. Can't be outside A or B, but as long as it's in one of those areas, then it is in the union. Huh? How about the intersection? A intersection B or A and B, as I like to read it. The intersection, well, it has to be in both A and B at the same time. Okay. How about disjoint? That means that A and B is equal to the empty set, which we can visualize. And I said, usually we still draw them with overlap like that, but just to visualize it, we can have them separated like that, just to show that there are no elements in common. How about the complement? I think it was the complement next. Let me check. Intersection, the complement. Oh, I guess I skipped the complement. But the complement, anything not in A, for example. I have A and I have B in a universal set. Everything that's not in A is in the complement. It's allowed to be in B, but not in that overlap. Let me just PQ and R. Okay. Do you think you could draw your way to the previous answer, where we worked our way through all the notation and stuff like that? You can do it, whoops, or we will do it. So we're now going to solve this by drawing. It's a little bit sneakier because it has 3 sets. And let's start there. P, Q, and R, because the universal set, I'll draw it nice and big here, is in a rectangle outside. So what we're going to do is we're going to have a circle for P. We're going to have a circle for Q, and we're going to have a circle for R. Each of these colors is going to go in one of these spaces, right? We can't list them in multiple spaces. So as I go through these colors here, red is in P and red is also in Q, but I don't see it in R. Okay. And so that means that I need to list it in that overlap, but it's not in the set R. Gets confusing because I used R and R, but that's okay. I'll clarify red. I guess I could have drawn, sorry. Let me draw better circles. I just need to be patient and let it snap into place like that. Copy. And I know seems easy, right? Well, it is. I don't know why I don't do it more often. There. P, Q, and R. So here I'm going to put red. It's in the area where P and Q overlap, but it's not in R. Now I'm going to cross red off the list for the universal set. Working my way through P. How about yellow? Yellow I see only in P, which means I'm going to list it in here, but only in P. This there. And now, why am I crossing it off of the universal set? Because I've already listed it, right? And so, or put it on in the circle. And so I don't need to put it on the outside. I need to keep track of which ones go on the outside. How about blue? Blue, I only see blue in P. So it's also on the outside. I'm going to cross that off here. So now I've kind of distributed all the elements in P onto my graph. How about Q? Well, we already did red. Moving on to green. Green is in both Q and R. And so Q and R overlap is here, green. And I'm going to cross it off the list for the universal set. Moving on to R. R has orange, which I haven't done yet. And so orange goes in just R. Cross that off. Green I've done already. And indigo, I haven't done indigo yet. Indigo goes in the set R. keeping track of my universal set, I see that violet is the only one that is outside of all these circles. So then I'll put violet over here. Now, usually it takes a little bit of time to sketch these out, and you might have to do multiple iterations, right? Kind of, okay, so if it's P or Q, let's start there. P or Q is this circle or both, right? But then I want not that. So then my colors that are outside those two circles are these three colors, right? But then I also want the ones that are not in R, right? But these guys are in R, and so I remove them, and I'm left with violet, which is what we found, right? So you can kind of, it takes effort to map them out like this, but then you can kind of look at it and get to where you want to go. I'm trying to think if, so to me, but I've done a lot of set work, and so it's hard for me to see if there's any other way to read this, right? If you read this, I don't see any other way to tackle it. P or Q, negate it, negate R, join them up. Think about it. If there's another way to read it that doesn't get you to violet, because that's the problem. I'm fine if it gets you to violet, but I can't think of any. Suppose a survey of car enthusiasts showed that over a certain time period, 30 drove cars with automatic transmissions, 20 drove cars with standard transmissions, and 12 drove cars of both types, because we are allowed to have more than one car. Probably hard to find one car with both, though, / impossible. But we can have more than one car. If everyone in the survey drove cars with one of these transmissions, how many people participated in the survey? Okay, this brings us to our counting aspect. Okay. I would probably do a Venn diagram, map this out. And so you've got your universal set of car enthusiasts. And you have some number with automatic transmissions and some number with standard transmissions. Right? Now these circles are representing my sets. In fact, I'm going to be talking about the count in each, or the number of elements in each set, rather than the elements themselves. So what I know from the question is that this total circle, right, this total circle of A has a count of 30. And this total circle of S has a count of 20. But there's overlap there, right? So we need to adjust for that overlap. Okay. And so we're told that 12 drove cars of both types. So I'm going to put that 12 in the overlap, but that means that, and I'm going to bump this up here, 30 minus 12 is 18. Math's not coming. And oops. 20 minus 12. 8. Because really what I want is I want each slice to be its own number, right? I don't want to talk about this overall circle, because then if I want all of S, for example, I can just take 12 plus 8 and add up the components that I want. So each piece, can I call them pieces? Each piece has a count that excludes the overlap. So when you solve these problems, okay, what you're going to do is you're going to start in the innermost overlap, right? And you're going to write down that number, and then you're going to take it away from all the other overlaps, right? And kind of work your way out. And so when working with Venn diagrams, we start at the innermost overlap and subtract that count working out. And that's so that you're not counting elements twice. Right? We quickly graduated to, this is the number of elements, right? Not the individual elements. That's okay. If everyone in the survey drove cars with one of these transmissions, what does that tell us about this outside area? Has a count of 0. Nope, not the car enthusiasts. How many people participated in the survey? It's going to be 18 plus 12 plus 8, right? Because if you did the 30 plus 20, well, another way you could do it, as long as you subtract the overlap, right? You could do that. To find the number of people surveyed, we have 18 plus 12 plus 8, which is 38. I'll do it in red. Notice this is not the same as the original 30 plus 20 equals 50, right? Because then we've counted the overlap twice. Here, we count the overlap twice. So an alternative is that A or B, which is what we want, is going to be A plus B minus A and B. That should look more like a, right. can add them up and subtract the overlap. But as soon as we get into 3 sets, which we will pretty quick here, then the formula becomes too messy. And it's going to be a lot easier to just visualize it with a Venn diagram. Right. So 38 people were surveyed. How about this? A survey of 100 people in California indicates that 60 people have visited Disneyland, 15 have visited Knott's Berry Farm, and 6 have visited both. How many people have visited neither place? Slightly different because now we're allowing for people outside these 2 sets. If I think about Disneyland as 1 set and Knott's Berry Farm as, which actually up until today when I read this, I thought was Knott's Berry Farm, but just shows I haven't been there. And the Universal set. Right. So how many people have visited neither place? We want to find what this count is. Because the total needs to be 100. So, like I said, I think the best way to tackle these is probably not the way I started, right? Where I put down the individual counts and then I subtracted. Instead, I would start in the most overlap, right? And I'm gonna jot down a 6 here. So 6 have visited both. So now I already have 6 out of all the D's accounted for, which means that I have 60 minus 6, gonna go for 54 that have only been to Disneyland. And 9, right? 15 minus 6. So 9 have only been to Knott's Berry Farm. Which makes this outside area 100 minus 54 minus 6 minus 9, which is something. $31. Californians have not been to either place. Have visited neither. I was hoping. Oh, Emily, can we please do one with 3 now? Yes. Finally. That's all I've got too. Lots of time for homework. And there's 2 pages of homework today. Okay. A survey of 100 exercise conscious people resulted in the following information. 50 jog, 30 swim, and 35 cycle. 14 jog and swim, 7 swim and cycle, 9 jog and cycle, and 3 people take part in all 3 activities. Now it's tempting to tackle all these, the problems that follow, But let's map out our Venn diagram first and get all this information on the plate. Yeah. And just like before, right, now we've got 3 sets. Let's start by making this nice and big. No. I think if I draw faster, it'll kind of clean up my box, but that's okay. Usually, I list the sets in the order that they appear because otherwise it gets really confusing. And so I'm going to let this first one be jog, and then this next one be swim, and the last one be cycle. And just like before, you're going to want to start. So these questions, we always list them the same way, right? The individuals, the 2x2s, and then all the entire overlap, right? All 3 activities. So how you're going to want to map these out is you're going to want to take, basically read it from the bottom is a good place to start. Because at each step now, right? Jog, swim, and cycle, there's 3. Jog and cycle is going to be this overlap here, but I already have 3 of those guys. And so in this area, I have, nice, 6. Swim, so 7 of them swim and cycle. I think the hardest part is just figuring out which overlap you want, right? Swim and cycle 7, but I already have 3, so I'm gonna put down 4. 14, jog and swim, but I already have 3 of them, so I'm gonna leave 11 that only jog or swim, right? Not cycle. This is where I'm going to need a calculator because I need this entire jog circle to add up to 50, right? So I need to chip away what I've already listed. So 50 minus 11 minus 6 minus 3. Oh, not divided by 3. Oh gosh. Let me start over. 50 minus 11 minus 3 minus 6. I get a nice 30. If I do the same thing for swim, they have to add to 30, but I need to take away 11 and 3 and 4. 12. And cycle adds to 35, minus 6 minus 3 minus 4. 22. Who have we forgotten about? The ones outside. We know the total is 100, right? And so what I'm going to do is I'm just going to subtract each of these individually. Right? It's annoying, but I think it's probably the easiest. 100 minus 30 minus 11 minus 3 minus 6 minus 12 minus 4 minus 22. I get 12 on the outside. It might be nice to just check those numbers before you go ahead and use them, but let's assume that they're good. And so now we have all our numbers of elements in each of the sets. And now we can answer questions. How many jog, but do not swim or cycle? Right. So they have to jog, right? So they have to be in this circle. but they can't swim and they can't, okay, they can't swim and they can't cycle. They don't. They probably can. But here it's easier to see that the answer is 30. How many take part in only one of the activities? Right, and one of these 3 activities, right? We're not talking about the outsiders, these guys. What could they possibly be doing?
Running.
Isn't it jogging?
Oh, that's
Oh.
different.
Ah,
Also walking.
you know what? They would differentiate between jogging and running. Okay. I don't jog. So they can only be in one area, but they're allowed to be joggers or swimmers or cyclists, right? And so we put in all that work for the Venn diagram, but now it's really paying off. Because now we can just look at it and grab the numbers that we want, 64. And how many do not take part in any of these activities? We already did that work. Nice. And now, I don't think I had any more. That's it. Time for homework, if you want. I'll stop the recording there, though. If you have any questions, let me know. Otherwise, enjoy your weekend and Pi Day tomorrow.